Hi students. So in the previous sessions, we have discussed about coordination complexes, how that was discovered by Werner, and the limitations in the valence bond theory, followed by how the CFT theory got evolved. And we also looked at the d orbital splitting. As you make a recollect, you have a degenerate d orbitals in the presence of electrons coming in the uh, uh, two different subset of d orbital, that is T2g and Eg. You are seeing the splitting of d orbitals. So in the last session, I talked about T2g Eg, which is T stands for triply degenerate d orbitals and Eg stands for doubly degenerate orbitals. And in that session, I also told you that the G stands for current, that's a symmetry element, which I said I will discuss later. So today we will discuss about what is G. And I also want to have a quick comparison of this d orbital splitting when you have a octahedral ligands, in this case on the right hand side of this. Whereas in the case of tetrahedral field, as always, this is plotted against the y-axis in the energy, right? So in the tetrahedral complexes, all you have is like your four different ligands are approaching the metal instead of six in the case of octahedral complexes. So this d orbital splitting delta, this O stands for octahedral complex, whereas this delta T, this d orbital splitting in the tetrahedral complex. So this magnitude will change. So delta has some numbers basically, which is coming from an experimental through various experiments. So that is not of your concern, but don't think that this delta is like always a constant. This is a variable depending for each different complexes, the delta O is going to be different. Okay. So in the case of octahedral complex, we said gyrate. Whereas if you look at this, tetrahedral field, this is completely opposite. Whatever the Eg, which is destabilizing in the octahedral complexes, whereas in the tetrahedral complexes, this E or set of orbitals is going to stabilize this. It's a simple comparison. So T to G is stabilizing here, T to G is destabilizing here. Eg is destabilizing here, Eg is stabilizing. Okay, so this is the first difference across the octahedral complex is a G, the gyrate. The second difference is whatever the orbital stabilizing in octahedral complexes is going to destabilize in the case of tetrahedral complexes. Okay, so these are the first two things we have to keep it in mind. The third thing is a way of representation, delta O and delta T. Okay, that stands for the respective geometry of the complexes you're going to deal with. Okay, so what is this gyrate? Okay, this G stands for symmetry. So let us have this look. This is a metal. You have 6 dots, okay, or 6 points which is approaching the metal. So the gyrate stands for, let me put, I will oversimplify the concept just for you to understand. For this you have a metal, right? So you travel the distance, okay, up towards the x-axis. So you find a ligand, some ligand. So likewise, from the metal, when you travel opposite direction, you also find some metal. Hope you understand the point. So from the metal, whatever the distance you are traveling up, when you are traveling down, in both the cases, you are witnessing a ligand over here. Okay, so this is on not only on the top and the bottom, left hand side. When you travel across this left hand side, okay, let's say distance d. When you travel on the right hand side, again the distance d, you see ligands on the left hand side also, on the right hand side also. Okay, so if you just from the metal, you're traveling from here to here, in the opposite direction in the y-axis you travel. So in both the cases you encounter the ligands. So top, bottom, left, right, on the other directions also, wherever you go up and the opposite direction, you always find the ligand. So this is a oversimplified version of telling the symmetry is present. So this symmetry is present. That is the reason why we put the letter G. Okay. Whereas in the tetrahedral complexes, as we have talked about here, there is no symmetry element. For example, you travel, up. This is a metal. You have the particular ligand over here. Okay. So so you just have to look at the in the three-dimensional way. So I have three ligands, okay, from here and one on the top. Okay, so you have to visualize. So whatever is in the top, I have some ligand. Okay, when you travel to the bottom, you will not find the ligand basically. Okay, so from there, from here to the opposite direction, you will not. So one direction you will find the ligand, the other direction you will not be able to find the ligand. For example, in here, if you can see, you travel from here to here, you find the ligand. From here to you just travel in the opposite direction, you won't find the ligand. Vice versa. So in this case, you find the ligand. When you just travel exactly opposite, you won't find the ligand. So this is a oversimplified concept of symmetry element present in the octahedral complexes, which is not present in the tetrahedral complexes. Also, if you notice that the D or the splitting gap, okay, this delta O and delta T, this is actually measured by a number of 4/9. There is a correlation between delta T and delta O by a factor of 4/9. So always octahedral complexes splitting, d orbital splitting in the octahedral field will be always higher in general compared to the tetrahedral complexes. Okay. So these are the general thing one have to always remember. It is also easy to benchmark and compare tetrahedral and octahedral complex in the same figure. So if you are able to remember this particular figure, you will be able to write all possibilities of octahedral complexes, tetrahedral complexes. Always, when you calculate CFSC, you always put the number of electrons. You fill the number of electrons in the orbitals. For example, in octahedral complex, you can put 6 ligands, okay, in the low spin complexes. So this stabilization CFSC numbers calculations will be completely different. Whereas in this case, you have E, that is 0.6 as a stabilizing factor. Okay, in this case, the numbers is going to be completely different. So if you remember this master diagram, I would say, so with this remembrance, you will be able to calculate very clearly for the octahedral complexes, tetrahedral complexes, CFSC calculations, spin only magnetic moment calculation, provided you know which ligand you are dealing with, like if it's a weak ligand or a strong ligand in the octahedral complexes. And in tetrahedral complex, you don't even have to worry about ligand. I will just tell you why. So what we have observed in the high spin complex. High spin complex means what? You have more unpaired electrons. When you have more unpaired electrons, that your splitting is very small. For example, you have a d5 system. Okay, let's say. So the first electron goes to E orbital, that is, let's say dx square minus y square. The second electron goes to dz square. The third electron has a possibility of either pairing with dx square minus y square, or it can go up to the dxy and yz. Because in the tetrahedral complex, the splitting is very small, this is something equivalent to a weak ligand in the octahedral complexes. Okay, this delta is small, so the third electron can just always jump up, okay, so that it will be like unpaired electron. So this is governed by a pairing of electrons within a given orbital comes with a energy penalty. Okay. So because these tetrahedral complexes are always lead to a smaller splitting, okay, compared to the octahedral complexes, you always end up high spin complexes in the tetrahedral complexes. It always forms high spin complexes. Why? Let's say again in D1, it is going to EG. It has a stabilizing factor of 0.6, right? How do you calculate the spin only magnetic moment? The formula of square root of n into n plus 2, where the n stands for the number of unpaired electrons. In this case, it is 1. So n is 1, 1 into 1 plus 2, that is square root of 3, that is 1.73 is the value, you get it, right? So this spin only magnetic moment, how many number of unpaired electrons, you substitute that with the simplest formula, square root of n into n plus 2, where n is nothing but the number of unpaired electrons. So when it comes to the CFSC calculation, so EG, that is 0.6 stabilization happened in D1 system. D2 system, you have minus 1.2. So 0.6 and 0.6 coming from two different electrons, unpaired electrons. So the D3, instead of pairing here, it just goes to T2G because the gap, delta T, the splitting of d orbitals is smaller. So the third electron always, tend to go to T2G, irrespective of whether the ligand is a stronger or weaker ligand. Okay, this is something very, very important. So with very few exceptions, all octahedral complexes form high spin complexes. Okay, so in this case you have D3. All you have is 0.12 stabilization, 0.4 destabilization, net CFSE stabilization in is 0.8. Okay, whereas in the case of D4 system, you have a stabilization of 0.4. This D5 system, here the CFSE is 0. So what 0 means, if I'm bringing one metal and 4 electrons, okay, and theoretically form a tetrahedral complex, okay, for let's say for D5 system. Since the complex formation is not going to give me any stabilization here. For example, in this case, before the complexation and after the complexation, there is an energy difference, that is 0.4 stabilization happens. But in this D5 system, okay, there is no crystal field stabilization energy. That means there is no bond formation. Basically, you have very likely that the complex formation is happening. Okay, because there is no stabilization. So the metal can remain as metal, the ligand can remain as ligand. So if it has to come and make bonds and form a new complexes, obviously it should be more stable and less energy. If that energy is not stabilized, there is no need of forming these bonds and new complexes. So it comes for D6 system. So now we have no other choice, just that the pairing happens. So in this case, you have minus 0.1 each stabilization and 1.2 destabilization. So you can look at this all this calculation. So the only point I would like to really emphasize with respect to the tetrahedral complexes is, irrespective of whether the ligands are weak or strong, their tetrahedral complexes will form high spin complexes. The reason is because the tetrahedral complexes delta T is the splitting energy. Okay, this smaller compared to the octahedral complex. So the correlation between delta T and delta O is a magnitude of 4.9. So we have a standard formula that can be discussed as we go along. So we also have square planar complexes, which is not part of the syllabus. Okay, but the square planar complexes, though it is 4 electron once again coming with respect to the metal, there the splitting of d orbitals are quite complex. Okay, so that just gets splitting. Now it's not that always the d orbital has to split into 3+2 fashion. Okay, this happens in octahedral complexes, it happens in tetrahedral complexes, but in square planar we have some new concept called Jahn-Teller distortion and so on and so forth, where the splitting will be like little more complex. Okay, so that is not part of the system. So you should always remember that the spin only magnetic moment calculation. So in this case, we are only calculating spin only magnetic moment, and this there is no pairing energy. Sorry, in the CFSE, we only give the numbers. We didn't usually mention the pairing energy. But for the sake of clarity, whenever there is a question asked for the CFSE calculation, you can always put, let's say in this case, minus 0.16 plus one pairing energy happens. Okay, in all this five, there is no pairing happens, whereas in this case, you have one pairing energy, 2, 3, 4, and so on. Okay. So with respect to the CFSE calculations, always be careful when it compares for the octahedral complexes. You have T2G as a stabilizing, and the first electron comes to the T2G, not to the EG. So the very first electron always comes to the stabilization zone. That is T2G in the case of octahedral complex. E, only E in the case of tetrahedral complexes. Okay. So this is what you have to always remember.